Okay, second video on synthetic geometry in our course 595, Teaching Geometry from a Problem-Solving Perspective. In the first video, we went through place to start in synthetic example 1. Let's take a look at synthetic example 2. So suppose that points A, B, and C are points on a circle with a center D. What geometric relationships exist between angle ABC and angle ADC? Okay, so this is a complicated statement, hard to visualize. I think the first thing we need to do is to get a sense of what we're looking at. So let's go to GeoGebra and see if we can learn a little bit there. Let's go ahead and open up a new window and see if we can draw what it is that we're after. So we certainly need a circle. We're told that there are 3 points on the circle. There they are. I think A, B, and C are the points on the circle, so let's go ahead and change those. I should probably change my view here in terms of font size. Let's get it to 20, maximize this. Move this point up a little bit. Okay, I think the circle is centered at D, so we're going to call this guy D. And so that one's D, and then A, B, and C are on. So this one we're going to rename. I'm right-clicking and renaming this one A. Hit OK. Let's just take a peek then to see if I have it right. A, B, and C points on a circle center at D. We're looking at the relationship between the angle ABC and ADC. ABC. So let's go ahead and draw in ABC. A to B and B to C, and ADC, so that would be this one, A to D and D to C. Okay, and the angles we are after, I guess, are, maybe put it at this point, this angle ADC and this angle ABC. And the question is what relationship exists between those two angles. Of course, we could draw these up and measure them on a piece of paper, but it might be kind of fun to let the technology do the work. Let's go ahead and load the angle measurement for ADC. We're going to call that the central angle. And I want just this to be the value of that angle. And then let's see this one. Oops, we need to get the angle measurement tool, A, B, C. Okay, well, so you need to know that angles are measured in a clockwise fashion. I went, I guess, counterclockwise fashion on GeoGebra. It's measuring the compound angle, or sometimes called the reflexive angle at B. That's not the one I want. I want the interior angle. So I think I must have to start to name them in the opposite order in order for the interior one to pop up. Let's go ahead and move that into the angle where we can read it, I guess. And I want to also change the label to just the value. And there you have it. You have the two angles that we're supposed to be looking for a relationship, and it sort of pops off the chart right away. This one appears to be half of that one. Let's just see if that relationship holds. If I move, sure does. Both of them change. This one's 86.19, 43.1. Interesting. Okay. So those are the two angles. One way we can check this is we can use the input bar at the bottom of the page to carry out any mathematical computation. In this case, what I'd like to see is what's alpha divided by beta. So I'll go down here, and since my keyboard doesn't have an alpha in it, I go over to the right here where the symbols are, and I just say, well, what's alpha? There it inputs the alpha. /, which is division, beta, and just hit enter, and it adds this number to the left-hand side of the screen, which is 2, and that number 2 is the calculated ratio of these two numbers, alpha and beta. And you notice what we really should be watching is that the number 2 doesn't change. One interesting, maybe something you might be able to use in your classroom is to use a text box with dynamic entries. So what we could do here is we could insert, to make it just absolutely clear, what is alpha divided by beta. So I'll start out by just typing in alpha divided by symbol beta, and I want that to be equal to, but here I want the object to be in there. Well, what is alpha? Let's put alpha in there, and you're getting a preview down here. And then I'll put in the text divided by, and then object beta. Difference between a symbol and an object is actually a value calculated to your to the text box. So you can see it's just picking out the numbers 70.6 and 35.3 from alpha and beta and putting them on in the text box. And then what we want that to be equal to is the object. I think it was the number A, which is 2. We hit OK, and it puts the text on the screen, or excuse me, in the graphics view. Usually I have to make this large for people to see it, but that's the idea, is that we want to see how those numbers change, and you can definitely see that alpha divided by beta is 86.22 and 43.11. But when they're divided, it seems like the division is exactly 2. It is interesting to watch sometimes the computer will struggle and you'll get a 1.99999 here or something like that because of round off error. But at this point, it looks like we're not seeing that much. But I see as C moves around that circle that the ratio of 1 to 2 doesn't change. Well, what about if B changes? Here it's very interesting. Notice that as long as I don't change where A and C are, that actually the angle at B and the angle at D don't change, which I think is a fascinating feature. In other words, as long as the two angles subtend the same arc of the circle, their values are constant. So the only way that we can really change the angle at the center of the circle, what we might call the central angle, and the angle on the circle, or what we might call the inscribed angle, is to change actually one of the legs, the vertices, the vertex that defines one of the legs of the angle, and not at the vertex of the angle. It does appear that there are kind of 3 different cases to prove here. There's this case where D, the central angle, is within the angle that we'll call the inscribed angle. There's also this case where, well, what happens when D's outside? You know, like if D is, does everybody see that D is outside? It might help us to put some color on this. So let's color the central angle here a different color. How about red? Let's pump up the size on it a little bit so we can see it well. Let's color the inscribed angle. Let's make it maybe blue so we can really differentiate these a little better. And that way we can really see them better. We could probably color the angles as well. Instead of making that one green, let's make that one blue. Instead of making this one green, let's make it red so that we know what it belongs to. And now you can see there's sort of these 3 cases. The red angle, or D, the vertex, is inside the, I guess, the edges of the inscribed angle. There's also this case where D is outside, right? You know, where we're like this. D is outside. There, D is outside as well of the blue angle. And then there is this sort of, well, it could be in, it could be out, or it could be on, right? There's a possibility where D could actually be drawn right on, you know, that angle. And that's, of course, the case when BA, what we're seeing here is BA, is a diameter, right? Because if D is on the inscribed angle, then what we have there is BA is a diameter, right? And so some interesting different settings that need to be proved. Obviously, a much more complicated proof would be called for here, one in which 3 cases would have to be proven to show that it's universally true. It's true in this case when D's inside, it's true in this case when D is outside, and it's true in this case when D is on, in each case the inscribed angle. Okay, so I think we have a good sense of what we need to prove. I'll go ahead and save this so that you can play around with it in your in your studies and learn from it. One thing I thought would be neat to show you is that you can animate these points too. Instead of you picking how to move them, you can just right click on them and hit animation on, and of course it'll just move the point around whatever object it's restricted to. Here we see the compound angles being measured, which isn't so nice, but there you can see that even as this thing moves around the circle, I guess it doesn't work when it's on a compound angle, but anytime it's measuring the correct angle, the interior angle of the intended angle, I guess, that we see that ratio of 2 being preserved. The controller too, by the way, pops up here on the lower left, so whenever you want to stop it, you can pause it here using the controller, and we'll just pause it. I do want to make it clear to you that, you know, the point, in order to be animatable, has to be restricted to you know, another object. So I could animate this one, or I can animate this one. Now B would be an interesting animation because you see B is controlling the diameter of the circle. So if you watch what happens when you animate this, well, you don't even get the option to animate it when you right click on it. And the reason for that is that B is not restricted in any way. Its path isn't restricted, so it can't be animated. Okay, so just a little lesson in GeoGebra there. Let's go ahead and switch over to the desktop and see if we can construct a proof of at least one of the 3 cases of this particular theorem. All right, can you see that all right? So hypothesis. Let's draw a picture here. All right. I'm going to try to use some color here just to make things a little bit more interesting. So let's see. Let's prove case 1, and then I'll leave cases 2 and 3. Let's see here. I'll do this one. Okay, so the inscribed angle, I'll say let's call this ABC. That one we think is half, is half the measure of the central angle ADC, I think we called it, didn't we? Okay, so let's go ahead and start with our proof. And let's make it clear to our reader that we're proving the first case, that is where D is on the interior. So case 1, D is on the interior of angle ABC. All right, so let's think about this. So I mean, at this point, what we really want to show is we just want to show that this angle ADC is twice the measure of this angle ABC. And we don't have a lot of artillery. I mean, in terms of what we can use, you know, we can use any of these proof cards and see if we can get at some sort of a reason, a rationale for why this incredible result actually happens. So let's think a little bit. I mean, right now, nothing really comes to mind much other than the fact that I know that since this is on a circle, that segment and this segment must be equal in length, right? So that kind of leads me intuitively to think like, well, maybe what we should do is draw in this segment right here. I'll draw it in dashed so it doesn't become too distracting in our drawing. But that segment as well must be equal in length because it's on a circle, and the definition of a circle is a collection of points that are equidistant from a center. Okay, so now I feel a little bit better because what I know is I've got an isosceles triangle there, an isosceles triangle there, and another isosceles triangle I could draw in right here. And I know quite a bit, well, not quite a bit, but I know some things about isosceles triangles, namely that these base angles are going to have to be congruent. Okay, so let's see. You know, what I'd like to show is that this angle right here is half the measure of that angle right there, right? So maybe I should draw it in. This angle right here is half the measure of that angle right there. Okay, all right. Well, maybe we should do a little scratch work and think about, you know, what's going on here in terms of the triangles drawn. So, I mean, what we have is sort of something, I'm going to just roughly draw this and think about it a little bit. We got something that looks kind of like this, where these are all the same. So if those are all the same, these are isosceles, I could call this an X, that an X. This would have to be a Y, and that could be a Y. It's not necessary that it be the same as that one. In fact, I think you can see that in the drawing. And then this one could be a Z, and that could be a Z, right? And if that's the case, then this big triangle here, we could say then that the angle sum for the big triangle is 180 degrees. So that would be 2x's plus 2y's plus 2z's, 180, factor of 2 in each of those. So I could have an x plus a y plus a z to be 90. So that's kind of interesting. If I take just one of these angles from here, and from here, that the sum always has to be 90. Well, what I'm trying to show is that this red angle is half of this, I guess, black angle or pencil angle. And the red angle's measure, of course, is the x plus the y, right? This guy is really the red angle. So what is x plus y equal to? Well, it's equal to 90 minus z. And that's interesting because that's relating the x and the y to just the z's in this triangle, right? But if I call this angle, I don't know, I mean, this is the one we want to relate it to. Let's call it, we can't call it C. I'd like to call it C because it's a central angle. Let's call it M for the middle angle. How's that sound? If I call this angle M, then in this little triangle, I can use the 180 degree triangle sum to say that M plus 2z's has to equal 180. So that means that M must be 180 minus 2z's. And there it is. I'm noticing what I have here is that x plus y, which is 90 minus z, relates to m because all I have to do is multiply this value by 2 and I get that value. So that means that this value times 2 must be equal to that value. Okay, I think that's the scratch work we need. So this is my scratch. I do this because I want you to realize that, you know, proofs don't just sort of miraculously, you know, coalesce out of the air. In fact, one of my favorite teachers used to do this, you know, this scratch work side of the proof and then a formal presentation of the proof. I think it's a good strategy, you know, when you don't have time to let kids find the proof for themselves. If you are presenting a proof, modeling it, to model that there's this sort of, you know, feeling your way around in the dark that goes on when you're trying to construct a proof until you sort of see the light at the end of the tunnel. And once you do, then you go back and you write a formal presentation of it. All right, so let's go ahead and see if we can make this happen. Okay, so what are we going to do first? We're going to construct segments BD and AC. Okay, so BD and AC. Once we have those segments constructed, note that since A, B, and C are all on a circle centered at D, we can state what? Well, we first want to state that all of these lengths are equal, so we can state that BD must be equal to AD must be equal to CD. There we go. So we've justified those marks as marked. In the figure. Okay, so we've got that. Now, notice that triangle ADB, triangle ADC, and triangle CDB are all isosceles. So their angles opposite congruent sides are equal in measure. They're congruent, so they're equal in measure. These angles have been marked with measures X, Y, and Z. Okay, so what did we do over here? I'm just sort of, X is up here, so we'll call that X, that one X. Y's down here, Y, Y, and then Z's here and here, Z and Z. Okay, so those are the angle measures, X, Y, and Z. Now we're going to use the triangle 180-degree angle sum on the big triangle ABC. So in triangle ABC, the sum of interior angles must be 180 degrees. So X plus Z plus Z. So that's 2X plus 2Z. No, sorry, that's a 2Z, not a Z. I did a 2 and a Z together. 2Z and 2Y must be equal to 180 degrees. Or just X plus Y plus Z must be equal to 90. That's a surprising fact in itself. I don't know if it is to you, but I mean, if I take one of these angles, one of these angles, and one of these angles and put them together, I'd form a right angle. Solving for X plus Y, we get, here I'm going to use a little color, X plus Y must be equal to 90 minus Z, okay? So if we solve for the X plus a Y, what we've really done is we've solved for the measure of the red angle, and it's 90 minus Z. Now what our goal here now is to show that the central angle, which we're going to call M, has a measure that's twice this. So now focusing on triangle, let's see, it's triangle ADC, and we're going to call this the M for middle angle. We again sum the three interior angles to get what? Well, we get X No, we don't. I just looked at the drawing. It doesn't have any x's in it. It's got two z's and an m, right? So it would be m plus 2z. That's going to sum to 180 degrees. Solving for m, we get m is going to be equal to 180 minus 2z, or just, let's make it completely clear, we want to show that it's double that. So what I think would be a good idea would be to factor out the 2. M would be equal to 2 times 90 minus z. And I don't know, at this point it's fairly evident to me, but maybe what we could do is sort of summarize it. So we have shown that the central angle is twice the measure of the, I guess, inscribed angle, the one that's red, as desired. And I think that's the end of case 1 of the proof. In case 1, we were able to show that that inscribed angle is indeed half the measure of the central angle. And let's kind of review what we did. Interestingly here, there's no congruence of right triangles, or excuse me, of triangles at all. It's basically, you know, the thing that plays the big role here is the isosceles base angle theorem. I guess we used this fact that 2 points determine a line segment array, so we used some construction. And then what else did we do? We used the definition of a circle to find some congruent segments. And there's one more, the triangle interior angle sum, right? So those pieces of information were all put together and used here to construct this. Let's go back and kind of make sure that we can see. We constructed segments, so that was, you know, given 2 points, we can construct a segment. So we're relying on one of our previously assumptions here. I guess it's a postulate. Let's see, we used the definition of a circle, right? On a circle, so on a circle. So we used the definition of a circle. We also said used isosceles triangles, base angles, right? Angles opposite congruent sides. And then, oh, sorry about that. Am I still live? And let's see, sum of interior angles of a triangle. We used that, and I think we used that twice, right? Sum of 3 interior angles. So triangle, 3 interior angles, sum. And then there was a little bit of algebra, you know, going on here too. We definitely had to make some cases with algebra. So I just want to make it clear that you know, the way that synthetic geometry proceeds is usually, you know, you have a certain number of theorems and definitions and axioms and postulates. These things are like tools, right? These are the things, the wrenches and sockets and screwdrivers that we use to operate on new objects and gradually build up our repertoire until this stack of known theorems really gives us, you know, lots and lots of tools to attack any sort of relational conjecture or hypothesis. One last thing I should make clear is that we're not done, right? I mean, in terms of what we noticed on GeoGebra, this holds for when that central angle is contained within the inscribed angle or outside or on. So let's just make sure that you're, you know, remain to be proved. And I'm not going to do it now, but there's 2 other cases that remain to be proved. I'll just say this. I need a piece of paper to write on because my desk is too bumpy. Remain to prove, let's see, this would be case 2. In this case, I think what we had was, something where, say, the central angle is this one, and the inscribed angle would be something like this one, so that the central angle is outside of the inscribed angle. And let's see, case 3 would be this case where the central angle and the inscribed angle, so that's the center there. So where the inscribed angle, the vertex of the central angle is actually on the inscribed angle here, right? And this one, the vertex of the central angle is outside. Of course, the case 1 that we proved was where this was inside the central angle. So perhaps I'll leave one of these 2 cases for your exercises this week. And please let me know if you do have questions, and I'll conclude the video now.